We've already looked at the idea that exponential functions can create scenarios where there's either growth or decay, and this all depends on the base. If the base is greater than 1, then there's going to be growth. If the base is a fraction between 0 and 1, then there's going to be decay in the total amount of whatever we're dealing with that's involved. But let's look at some actual examples of growth and decay in the real world. One of the first ones that we looked at briefly last time was the idea of interest. So let's imagine that we have $2,000 invested in an account that earns 8% interest that's compounded continuously. The key word here, continuously, tells us that we're going to use the formula that the amount that is in the account is going to equal the principal, the original amount, times e raised to the RT power. Well, if we've invested $2,000, that's going to be our principal amount. E is our exponential growth that we're using. R is going to be our interest rate in decimal form, so 0.08. And we want to know when is it doubled. So we're looking for a time here, but we don't have a final value. However, because it tells us that it doubled, we know that the final value is going to be 2 times the original amount, which is 2,000. And here's where our solving exponential steps come into play. We're going to divide both sides by 2,000, which leaves us with 2 is equal to e to the 0.08t. The way we undo exponentials is we're going to take the log of both sides. We could take a log of any base, but it's easiest we're going to find if we take the natural log of both sides. This leaves us with the ln of 2 is equal to the ln of e to the 0.08t. Using our rules of logs, we know we can pull this exponent out front, which gives us the ln of 2 is equal to 0.08t times the ln of e. We know that the ln of e is equal to 1, so we can ignore this value here, since 1 times anything is itself, which gives us the ln of 2 is equal to 0.08t. And if I divide both sides by 0.08, I get that t is 8.7 years. So in 8.7 years, the value of the account will double. Another area where you may see exponential growth is the idea of inflation. So let's consider a scenario where in 2018, the price of a pizza is $9. In 2021, the cost is $12. And if we know the growth is exponential, we want to know what the cost will be in 2027. Here, notice that we have to do the same calculation twice. We don't have a principal value here, but we do have a starting value. We can think of a generalized form of the equation as some value y is equal to the original amount, that's our a value, is going to be our original amount, times e to the k, which is going to be our constant, to the t power. So in this case, our starting value is going to be $9. That's the cost of the pizza in 2018. E to the k, and we know that between 2018 and 2021 that we have 3 years passing, so our value is going to be 3 here. And in 2021, the cost is 12. We're going to be able now to solve for our k value so that we can then go back and calculate the cost in 2027. I'm going to divide both sides by 9. 12 divided by 9 can be reduced to 4/3 is equal to e to the, I'm going to bring the 3 out front to make it 3kt. Or I'm sorry, 3k. Take the ln of both sides, and I have the ln of 4/3 is equal to 3k when I bring that exponent out front, ln of e. Remember, the ln of e is 1, so I can divide both sides by 3, giving me a k value of the ln of 4/3 divided by 3, which gives us an approximation of 0.09589. I do recommend you carry that out quite a few decimal places so rounding errors do not compound. And then we can go back to our original equation. We know the cost of a pizza is going to be the original cost, A, e to the 0.09589, which is our k value, times t. Notice our original cost does not change. It's still 9. And then we have e to the 0.09589. But this time we're going from 2018 to 2027, which is a t value of 9 years. And so we can calculate the new value for our pizza. Be very careful here when you plug this into the calculator. Make sure you include parentheses correctly so that 9 becomes part of the exponent. And you will end up with a cost of the pizza of $21.33. Last but not least, let's consider one where we're not given quite as much information. We're told that the demand for a product doubles every 8 years. That sentence right there tells us that this is some sort of exponential growth. So we know y is going to equal the initial value times e to the kt again, but we want to know how long is it going to take for it to triple. Again, the key part is we have to find this k value. Doesn't matter what a value we start with. So let's consider that we just start with a of some product and it's going to double in 8 years. Because it doubles, we know that our ending value is 2a, twice what we started with. So when we go through and calculate here, solving for k, we're going to divide both sides by a, giving us 2 equal to e to the 8k. Again, taking the ln of both sides, I end up with the ln of 2 is equal to 8k ln of e. That ln of e can be disregarded because it's equal to 1. And I divide both sides by 8 to get a k value of 0.08664. This then allows us to set up our equation, y equals a e to the 0.08664 t. And what we want to know now is we want to find the time that it takes for it to triple. So again, if we start with a and it triples, we know we end with 3a. The a's from both sides cancel. I can take the ln of both sides, giving me the ln of 3 equals 0.08664 t ln of e. Our ln of e disappears because it's equal to 1. And so when we divide both sides by the 0.08664, we get that the time that it takes it to triple is 12.7 years.